Please join me in welcoming the SEA's Earth from Space team.
Hi, my name's Hannah Lang, and I'm from Edmond, Oklahoma.
Hi, my name is Jordan Cochran. I'm from Columbia, South Carolina.
And we're 2 of 6 members of the 2020 NASA SEA's aerospace team. And today we're going to be sharing our team's design of the Synchronous Ecuadorian Ecological Satellite, or what we call the SEASat. So this past summer, our group from all across the country worked virtually as part of the SEA's program to create this presentation with the help of our mentor, Dr. Wallace Fowler. And we were originally tasked with creating a design that would protect Earth-observing satellites from space debris. So from this original idea, our team developed the mission of launching an ecological monitoring satellite into geostationary orbit. So now Jordan and I are going to share a little more in depth of our team's concept of the SEASat. So the mission of the SEASat is to monitor the ecosystems of several national parks throughout Ecuador so that the diversity of these ecosystems can be maintained. The parks are host to a wide variety of endangered species and habitats which face many threats from human intervention to natural disasters and climate change. So by using monitoring systems such as LiDAR and infrared technology, the CSAT will help to give us a greater understanding of the well-being of these parks, as well as to maintain the biological diversity of these ecosystems. So in addition to the Earth science capabilities of the CSAT, our satellite is designed to complete the duration of its mission from its launch to the end of its life without producing any space debris, which threatens the future of other missions. So with these goals in mind, the CSAT is centered around the idea of more environmentally friendly space, Earth science, and space missions for both the Earth and in orbit.
Space debris, also known as space junk, are human-made objects that are no longer functional and therefore are dumped into space. The main problem about discarding junk into space is that it could potentially damage other spacecraft that are in orbit, which they can move up to 17,000 miles per hour. Ever since Russia's Sputnik 1 evaded Earth's gravitational pull on October 4, 1957, scientists have not been able to find an effective method to properly dispose of space debris. This led NASA scientist Donald J. Kessler to propose the idea of the Kessler syndrome, also called the Kessler effect, in 1978. In this theoretical scenario, Kessler concluded that due to the high amount of space pollution, a cascade of collisions will form as a result. Once this begins, satellites and spacecraft will be at a high risk of crashing into debris while in orbit. Kessler theorized that this process would take 30 to 40 years to occur, which brings us to today's low Earth orbit at critical mass. We are designing our mission to avoid conflict with space debris and achieve our mission of studying and protecting the ecological aspects of Ecuador's national parks. The 3 national parks that we researched are Yasuni, Sangay, and Podocarpus National Park, which are all located in Ecuador. Yasuni National Park was established in 1979 and is known to be home to the equator, the Andes, and the Amazon rainforest. The park is considered to be the most biologically diverse site on the planet, with over 4,000 plant species and 300 mammal species. Over 20% of Ecuador's reserves come from Yasuni National Park because of its rich soil. Sangay National Park was also established in 1979 and is home to 2 active volcanoes, Tungurahua and Sangay. The park consists of 7 ecosystems: glacial/volcano ecosystems, cloud forests, the Amazon, wetlands, lakes, fragile moorlands, and highland grasslands. Lastly, Podocarpus National Park was established in 1982 and is located in Southeast Ecuador. Like Yasuni National Park, Podocarpus is filled with a high amount of biodiversity and is home to 4 rare animals. These 6 species all live in the national parks and are considered to be near threatened or vulnerable. The Amazonian manatees are a vulnerable species of mammals that live in the Amazon basin of Ecuador. They are known to be the smallest type of manatees and typically have a white or pink patch on their chest. The cause of depopulation amongst these mammals is illegal hunting, which has been widely popular since the 1930s. The spectacled bear, also known as the Andean bear, is a vulnerable species of mammals, and is the only bear native to South America. Spectacled bears commonly have black or brown fur with beige markings on their face and chest. Poaching, trophy hunting, and habitat loss are major contributors to the decline of the Andean bear. The pay-best stepfoot toad, like the spectacled bear, is a vulnerable species of Ecuador. The crested eagle resides in the tropical rainforest of Central and South America, and due to habitat destruction in Brazil, crested eagles are only found in the Amazonian basin. They are also hunted by the locals because they perch for extended periods of time. Today, the bird species is listed as near threatened according to the International Union for Conservation of Nature, also known as the IUCN. Along with the crested eagle, the cerulean warbler is a near threatened bird species. The margay is another wildlife species that is also considered to be near threatened by the IUCN. It is a small wildcat that is similar to an ocelot, but with larger eyes and a longer tail. The main cause of the population decrease in the species was illegal hunting for trade up until the 90s. And as of 2008, deforestation and loss of habitat is the main factor of the margay's decline. Unfortunately, it is difficult to reproduce more margays because cubs typically suffer a 50% mortality rate. The main three threats to Yasuni, Sangay, and Podocarpus National Park are oil drilling, the Tungurahua volcano, and deforestation. Because of its rich oil reserves, Yasuni National Park is now at risk. The quest for crude oil began in the 1970s when seismic crews started searching for the park's vast deposits underground. The helicopters that carried the crews dropped dynamite onto the areas where the native tribes lived because they resided where the oil companies wanted to explore. Despite the protests of the indigenous people and environmentalists, these companies continued to venture out to Yasuni National Park. The Tungurahua volcano is the biggest threat to Sangay National Park because its eruptions are known to be violent to the surrounding area and its inhabitants. The volcano became active again on August 19, 1999, after being dormant for over 80 years. During the 1999 eruption, the residents of several communities had to evacuate and could not return home until a year later. In Podocarpus National Park, deforestation is a major issue. Due to the lack of environmental awareness, it has become complicated to solve this problem. Deforestation has been found to be more common in the lower elevations of the national park. Extinction of species, enhanced emission of CO2, and changes in landscape configuration are the after effects of deforestation.
So now I'm going to talk about the longitude placement of our satellite. So the CSAT will be placed into geostationary orbit, which we also call GEO, at a spot over Ecuador, which is represented by the red dot on the map in the right-hand side of the slide. And the satellite orbits the Earth in exactly the same time as it takes the Earth to turn once on its axis, which is 1 day. So because of this orbit, CSAT seems to hang motionless over this one spot, represented by the red dot over the equator. And the satellite altitude is about 5.5 times the radius of the Earth, and our instrument field of view is 3.26 degrees, or about 1,000 kilometers in radius. Because of this, a satellite over the red spot on the map can view all of Ecuador, including our 3 selected parks 24/7. So the CSAT will be launched from the Kennedy Space Center in Florida, located at 85 degrees west longitude or 275 degrees east longitude. To get to the right spot over Ecuador, the satellite and its booster stage wait in a low Earth orbit for 12.65 hours before starting to go up to geostationary orbit height. The rocket makes a first burn in low orbit and then coasts up to geo, and this transfer takes about 5.25 hours. At geostationary orbit height, CSAT separates from the lower stage and burns again, boosting its speed to match Earth's rotation. The lower stage performs a reverse burn, slowing down so that when it comes back down, it burns up in Earth's atmosphere. The transfer from low Earth orbit to geostationary orbit also requires that we change the plane of the orbit around Earth. So we're initially in a plane that's inclined 28.5 degrees with respect to the equator, and our target orbit is at 0 degrees because it's in the equatorial plane. So the most efficient way to do this is to change the orbit inclination by 2.2 degrees at the low end of the transfer orbit and by 26.3 degrees at geostationary orbit altitude with the second CSAT burn. And then at the end of the mission, the CSAT will do a small 2-burn transfer to an orbit above geo, which is also called the geo graveyard, to make room in geostationary orbit for other satellites. So we decided to launch the CSAT from one of SpaceX's Falcon 9 rockets, again from the Kennedy Space Center in Florida. So the Falcon 9 fits our idea of sustainable space travel due to the reusability of many parts of the rocket, such as the boosters and the fairing halves that protect the satellite. Also, the Falcon 9 is significantly more cost effective in comparison with other rockets, especially as the cost to launch decreases when parts are reused and recycled multiple times. This rocket is also really reliable, and other missions have been able to reuse the first stage anywhere around 10 times. So you can see on the diagram on the right that I drew the stages of the Falcon 9 through its trajectory. So the actual rocket itself will be fueled by liquid oxygen and rocket grade kerosene, while the propellants for the first and the second burn will be solid. However, the fuel for station keeping while the satellite is in orbit and for the burn to get to the geo graveyard will need to be stored for the long term, as our mission could last anywhere upwards of 10 years. So we'll use either a storable hypergolic propulsion system, which means that the two components will react spontaneously without a spark, or we'll use a low thrust ion system. You can also see on the diagram that the satellite will be located in the fairing at the tip of the rocket. So while the payload to low Earth orbit on a Falcon 9 is over 22,000 kilograms, our satellite will only weigh 1,575 kilograms. And this mass includes the total capacity for all of the instrumentation on board the satellite. The total mass of 10,200 kilograms for these sections of the rocket come directly from SpaceX's Falcon User's Guide. The diagram at the right also shows the parts of the rocket that actually go into orbit. So the bottom part is a lower stage that does the boost from low Earth orbit to geostationary orbit, and the big fuel tank does that burn. This stage does not enter geostationary orbit, but falls back towards Earth after it reaches geo. And then the small fuel tank is used at geo to slow the stage down enough that it enters Earth's atmosphere and then burns up. The top stage carries CSAT, which includes all of the instrumentation on board, and its large fuel tank is used to put the satellite into geo. The smaller tank is used to move it to the geo graveyard at its end of life.
CSAT is an environmental satellite. Various instruments are used to monitor the environment from space. CSAT will use LiDAR, which is light detection and ranging, to measure topographic changes due to volcanic eruptions, erosion, and industrial encroachment on the national parks of Ecuador. CSAT will use infrared detector to sense the temperatures of air, water, vegetation, and bare ground. It can also provide information about water vapor in the air, cloud properties, and other weather information. CSAT will also have optical sensors on board. These sensors will provide information about weather, terrain changes, vegetation health, and can provide early warnings about fires. The satellites shown at the right of the slide have already flown with instruments of the types needed for CSAT. The name of the specific instruments on the satellites are given. Overall, CSAT is a satellite designed to protect two parts of Earth's environment. It is designed to closely observe a very environmentally sensitive area in South America while not contributing to the proliferation of orbital debris. We have conducted an initial evaluation of the basic design parameters for a satellite that will protect biodiversity, monitor effects of oil exploration in Ecuador's national parks, and minimize mission impact on orbital debris. Overall mission goal is to protect our home, our beautiful Earth.
So we're now each just going to talk a little bit about our personal experiences with the SEAS program, especially in our education. So for me, I've always been interested in aerospace engineering, but I'd never had much exposure to any of the field before. So through the SEAS program, I was able to learn some basic concepts in aerospace engineering, and as well as learn about a lot of different topics in earth science, which I found very interesting as well. And now I'm really excited that I'm going to be attending the University of Oklahoma to major in aerospace engineering this fall.
CSAT showed me what it is like to be an aerospace engineer at NASA and how challenging it can be. It has also confirmed that I truly enjoy working with rockets and learning about outer space. Next year, I plan to apply at Georgia Tech or FAMU and major in mechanical or aerospace engineering.
And now as we finish up, we just want to say thank you to a lot of the people who have helped facilitate all of our projects. So first of all, we have to say a really big thank you to our mentor, Dr. Fowler, for all of his time and his help that he shared with us throughout every step of our project. And we'd also like to thank the C's administration for giving us this opportunity to gain some firsthand experience virtually, as well as we'd like to say thank you to all of the other organizations that have helped to facilitate this program. So thank you for having us.
Great. So I have a question. What do you feel has been your biggest challenge as you were conducting your research last summer?
I can go first on this one. I'd say my biggest challenge was finding information, because sometimes if I was trying to Google like about the national parks, I couldn't find much information, so I had to dig around from website to website. But also understanding what I was learning, because before C's, I didn't know about any of the stuff like LiDAR, none of that. But now I have a general idea of what it is.
So I had some of the similar challenges with Jordan, which was really just that all of this information was completely new. But that I think made it more fun, just having all of these new topics that we got to experience. But I think one of the other challenges too was just figuring out how to put each step of the project together, just because we did combine so many different elements, which was really where our group came into play, that we all work together. But yeah, just finalizing everything and putting it together was a fun but challenging part of our project.
Another question is, can you tell us more about the different skill sets and sciences that contributed to your team's success?
And I would like to take this question.
Yeah, I can. So we did have a group of 6 people who worked together, so we did divide everything up a lot, but we all started by learning just some basic orbital mechanics, just with learning about different orbits and how we would use them with our project. And then from there, we all started looking more into the space debris problem. So we did a lot of different research into how space debris affects the future of other missions, and we decided to make that a large portion of our project and how we could avoid creating that. So researching that step was another large part. And then after that, one of our other skill set was the earth science side of our project. So we did work together. Jordan did a lot of the research on the different environments that we were working with, and how we would incorporate all of those different steps together.
And I think the last question, unless there's another one in the chat, outside of your research and your project, what was the one thing about the C's program that you found the most beneficial? Subject matter experts, the Earth and Space Science course, Python, anything like that?
I would say that C's has given me a general idea of what it's like to be an aerospace engineer and to know what I'm working with. So when I do get a job as an aerospace engineer, I have a general idea of what I have to deal with.
I would say for me, C's gave me a lot of new skill sets with working in these new areas of STEM within a group. So having our mentor help us was a huge benefit, and that's something that's really helped us not only during the C's program, but once it completed. So we've continued to work with our mentor, Dr. Fowler, all throughout this project. And as well as since we all kind of went into this project knowing pretty much zero and starting from there, we were all really interested in this project, and we were able to kind of bounce off of each other's ideas and our different skill set to work together, which was the really fun part of this project.
Well, it's obvious that you did a great job, and congratulations, and thanks for joining us today.